Friction plays a role in every mechanical system, whether it's gears meshing, pistons sliding, or bearings rotating. Anytime two surfaces contact each other, friction is there, resisting motion, whether you want it to or not. But what exactly is friction? What causes it? And how can we use it to our advantage? Let's find out. At the most basic level, friction is a resistive force that acts whenever surfaces are in contact and there's relative motion, or attempted motion, between them. Consider a block resting on a table. If you push on it with a small amount of force, it doesn't move, because a friction force develops at the interface between the two surfaces, exactly balancing the applied force and preventing the block from moving. As you increase the applied force, the friction force increases too, up to a limit. Push beyond that limit, and the block starts sliding. Let's plot this relationship between friction and the applied force. The friction force increases linearly as the applied force increases, up to a maximum value. Any additional force causes the block to slide, and once it starts moving, the friction drops to a lower, roughly constant value. There are two different friction types, static friction and kinetic friction. It takes more force to start motion than it does to maintain it. So what causes this resistive force between the two surfaces? It turns out friction is the result of some quite complex interactions that occur at the microscopic level. Even the most smooth-seeming surface, if you zoom in close enough, is covered in microscopic peaks and valleys, called asperities. When two surfaces are brought together, it's these asperities that make the first points of contact. Because the load is supported by just a few microscopic regions, the local pressures at these points get really high. For the two surfaces to slide against each other, the asperities have to deform or shear off, dissipating energy in the process. It's this resistance to motion, accumulated across millions of tiny contacts, that gives rise to friction. As well as the mechanical interaction of asperities, intermolecular forces come into play in regions where the asperities are in close proximity. Atoms from one surface form temporary bonds with atoms from the other, and these bonds need to be broken for sliding to happen. For very smooth surfaces, these intermolecular forces can be a big contributor to the total friction force. It's also these bonds that cause kinetic friction to be lower than static friction. When the contacting surfaces are at rest, there's time for more and stronger bonds to form between the surfaces, making it harder to start sliding than to keep sliding. Now consider two identical blocks, both placed on the same surface, but add a weight on top of one of them. If you push on both blocks, it's clear the heavier block requires much more force to overcome static friction. This is because the friction force depends directly on the normal force, the force that presses the two contacting surfaces against each other. For an object sitting on a horizontal surface, the normal force is just the weight of the object. The object pushes on the surface with a force equal to its weight, and the surface pushes back with an equal and opposite force. It's this force that determines how much friction there is between the two surfaces. On an inclined surface, the normal force is the component of the object's weight that acts perpendicular to the surface. A steeper slope will reduce the normal force, resulting in less friction. In a bolted joint, the normal force that determines how much friction there is between the two joined parts is the clamping force pressing the parts against each other. It's equal to the preload generated in the bolt by applying torque. And in a brake assembly, it's the force delivered to the brake pads by the mechanical or hydraulic system. The relationship between the friction force and the normal force is described by the Coulomb friction equation. F is the friction force, N is the normal force, and mu is the coefficient of friction. For a system in motion, this equation gives the kinetic friction force. For a static system, it gives the maximum static friction force. The actual static friction seen by the system is only equal to this value just before slipping. The coefficient of friction mu accounts for the nature of the two contacting surfaces. Let's look at some typical values for different materials. The difficulty with the coefficient of friction is that it depends on much more than just the materials involved, so these are all very approximate values. Surface roughness has a big impact because it affects the likelihood of mechanical interlocking at asperities. Even machined surfaces, with their directional textures, can have different friction coefficients in different directions. Then there's the presence of surface oxide layers, cleanliness, temperature, and even heat treatment that can all have an impact on friction. Because of all of these different factors at play, the coefficient of friction is an empirical parameter. It can only really be determined experimentally. This is often done using a device called a tribometer. The one shown here uses the pin-on-disc setup to measure kinetic friction. A ball of one material, the pin, is pressed against a disc made of a second material with a known normal force. The disc spins, and the frictional force is measured by the pin holder, allowing the coefficient of kinetic friction to be calculated. We saw earlier that friction depends on normal force. The heavier of these two blocks will see a larger friction force. Now consider a different scenario. Two blocks with the same mass, but different contact areas. How do you think this will affect friction? You might initially expect the block with the larger base to experience more friction, because there's more material in contact with the surface. But that intuition turns out to be misleading. In fact, the friction force is roughly the same for both blocks. This can feel counterintuitive at first, but makes sense when you think about the difference between the apparent contact area, which is the visible base of each block, and the real contact area, which is the sum of the microscopic contact points where the surfaces actually touch. When you increase the apparent contact area without changing the normal force, the contact pressure at the touching asperities decreases, meaning fewer asperities are pushed into close enough contact to interlock or form strong intermolecular bonds. The real contact area stays roughly the same, and as a result, so does the total frictional force. This is a general observation that applies to most contacts involving rigid materials, but there are definitely exceptions. For very soft materials like rubber, friction can depend on contact area because of how easily these materials conform to other surfaces. Another possibly counterintuitive aspect of friction is that it doesn't depend on the relative velocity of the contacting objects. Moving faster doesn't result in more kinetic friction, because the fundamental contact mechanisms, the deformation of asperities and adhesive bonding, don't depend on how quickly the surfaces slide past each other. These observations related to normal force, contact area, and sliding velocity are sometimes referred to as the three laws of dry friction. In many applications, the goal is to reduce friction as much as possible, usually to improve efficiency and reduce wear. One material well known for its low friction properties is the polymer PTFE, also called Teflon. It has extremely low friction properties thanks to its unique molecular structure, consisting of chains of carbon atoms surrounded by fluorine atoms. The fluorine shield creates an inert and slippery surface that resists adhesion to pretty much all other materials, resulting in very low friction coefficients. This makes PTFE a material of choice in dry contact applications, like plane bearings, where it allows shafts to rotate with minimal frictional resistance. So far, we've only talked about dry contact, but one of the best ways to reduce friction is the use of lubricants. Clean, dry steel sliding on steel typically has a coefficient of kinetic friction of around 0.5, but add a thin film of oil and it drops to 0.1 or less. Lubricants work by introducing a thin film between the two contacting surfaces, coating the peaks and filling in the troughs of the asperities. This minimizes mechanical interaction between the surfaces and reduces friction. The thickness of the lubricating film has a big impact on friction. When it's very thin, surface asperities still make contact, and although friction is reduced compared to dry contact, it remains relatively high. This is known as boundary lubrication. As the film thickens, a growing portion of the load is supported by the fluid. This is mixed lubrication. And if the film thickness continues to increase, it becomes thick enough to completely separate the surfaces, which is hydrodynamic lubrication. The relationship between film thickness and coefficient of friction forms a characteristic curve. Friction is high when the film is very thin, but falls in the mixed lubrication regime as more surface asperities are separated by the fluid. It then rises again in the hydrodynamic regime once the two surfaces are completely separated, because more fluid being dragged between the two moving surfaces means an increase in viscous shear forces within the fluid, and so increased energy losses. The same system can pass through all three regimes, depending on the operating conditions. Consider a spinning shaft inside a lubricated sleeve. When the shaft is still, there's no motion to draw lubricant into the gap, so metal-to-metal contact dominates, and friction is high. As the shaft begins to rotate, the relative motion between surfaces entrains lubricant into the contact area. This builds a thin fluid film, gradually reducing friction as mechanical contact between the two surfaces reduces. With increasing speed, the film becomes thick enough to fully separate the surfaces, entering the hydrodynamic regime. Unlike dry contact, with hydrodynamic lubrication, friction tends to increase with sliding velocity. This is because viscous forces within the lubricant contribute most to the total friction force, and these forces depend on strain rate, which is determined by the relative velocity of the sliding surfaces. Lubricants come in many forms, each suited to different operating conditions. Liquids, like oils, are ideal for high-speed machinery because they flow easily and continuously replenish the lubricating film between fast-moving parts. Greases, being semi-solid, perform best in applications where motion is slower or occurs only intermittently, or where the lubricant needs to stay in place without leaking over time. They tend to degrade more easily at high temperatures and high speeds than oils do. Most commercial lubricants contain additives like anti-wear agents, corrosion inhibitors, and viscosity modifiers to help the lubricant function reliably under a wide range of conditions. Not all engineering problems are about minimizing friction. In many cases, the goal is precisely the opposite. Car tires, for example, are designed to maximize friction because that's what gives a vehicle grip, allowing it to steer, accelerate, and brake effectively. This wheel is free rolling. It rotates at exactly the right speed to match how fast the car's moving, so there's no slipping between the tire and the road. At the contact patch, each bit of tread touches the road, and then lifts off again, with no sliding motion between the tire and the road. When the driver accelerates, the wheel starts rotating faster than it would during free rolling. To accommodate this increased rotation, the bottom of the tire would need to slip backward relative to the road. But static friction acts to prevent this slipping motion, exerting a forward force on the tire at the contact patch. This causes the car to accelerate until its speed matches the increased rotational speed of the tire. A similar thing happens when braking. The wheel is forced to rotate more slowly, so the bottom of the tire tries to slide forward. But this is opposed by a static friction force acting backwards, slowing down the car. If the forces applied by acceleration or braking exceed the maximum static friction force, when braking hard on a wet road for example, the tire begins to slide instead of maintaining rolling contact. At this point, static friction is replaced by kinetic friction. Because the tire can no longer be directed by steering inputs when it's sliding, and because the coefficient of kinetic friction is lower than the coefficient of static friction. This results in a significant loss of control. Increased friction between the tire and the road means increased grip and better control of the vehicle. Friction can also be used to amplify forces in surprisingly effective ways. Take the example of a rope wrapped around a post, a common method for securing a load with relatively little effort. The holding force required to secure a given load depends on two factors: the coefficient of friction between the rope and the post, and the angle through which the rope is wound. The relationship between these two forces is described by the Capstan equation. The fascinating thing here is that the equation's exponential. With a turn of just 240 degrees, and assuming a typical rope-to-metal coefficient of friction of 0.3, the post allows a 100 Newton pull on one end of the rope to hold back a 350 Newton load. That's a 3.5 to 1 force amplification. Use an extra turn of the rope, and the 100 Newton pull can hold back over 2 kilonewtons, meaning you could hold up the weight of 3 friends with one hand pretty comfortably. This principle has been used for centuries in nautical applications, allowing sailors to secure mooring lines or huge sails using nothing more than their body weight and a few turns of rope. Friction is a critical part of how mechanical systems work. It can provide useful grip, cause unwanted energy loss, or lead to damaging wear, making it something engineers need to understand and control. And it all depends on exactly how the contacting materials are structured at the microscopic and molecular scales. This fascinating connection between a material's internal structures and its mechanical behavior lies at the very heart of materials science, and is something I explore in more detail in Microstructure, a series of videos I've been working on that examines how the internal structures of materials can give rise to remarkable and sometimes unexpected properties. The most recent episode dives into the world of piezoelectric materials, materials with a unique atomic structure that produces an electric charge in response to mechanical stress. This unique property enables a wide range of technologies, from pressure sensors to ultrasound machines. You can watch this episode of the Microstructure series right now, over on Nebula, the independent streaming platform built by creators.